This video will be about the basis, dimension, and rank of a matrix. A basis is defined to be a group of vectors from the vector space that is linearly independent and spans that vector space. A natural basis is vectors in Rn wherein for E sub I is equal to 1 if the row is equal to that index and 0 if otherwise. So in the case of, let's say, R3, E1 has this vector, E2 contains this vector or is equivalent to this vector, and E sub 3 is equal to this vector. So for E sub I, it can extend all the way to n in size or in dimension, wherein 1 is when it is equal to that row. And then we also have the concept of a finite dimensional vector space wherein it's a finite subset of V that is considered to be a basis for that vector space. So one important theorem is that if S, a set of vectors, is a basis for that vector space, then every vector in V can be written in one and only one way as a linear combination of the vectors in S. So here, when we say that it is a basis, again, it should be linearly independent and also spans that vector space. So how do we show that every vector can be written in one and only one way as a linear combination? One easy example would be the zero vector. So if we have a linear combination over here, all the way until a sub n, b sub n, we know then that there is only one and only one way that the zero vector can be solved, wherein all the constants or scalars must be equal to 0. If it's not, then therefore it would be linearly dependent and therefore would also not be a basis for a vector space. So the fact that this has one and only one way to represent how to solve for the zero vector means that it is linearly independent. And in addition to that, it can also be used for other vectors as well. So we can represent it with like any vector v, and the constants, depending on whatever you choose, wouldn't point to the same vector. So depending on the constants that you choose, it won't always point to the same vector, wherein that would mean that all the vectors have one and only one way to represent each other. Another important theorem is that given a subset of non-zero vectors in a vector space, and a set W is said to be the spanning set, then some subset of S is a basis for W. This will be shown in our example here. We want to identify if the set of vectors is a basis. So we are given the set of vectors and are tasked to identify if they are a basis at R3. First, what we want to do is identify its linearly independent. And to do that, you first create the augmented matrix, wherein you have all the vectors at the left-hand side and the zero vector at the right-hand side. So we have 1, 1, negative 1, 2, 3, 4, 4, 1, negative 1, and 0, 1, negative 1. And on the right-hand side, we have the zero vector. Once we are able to get this, we then take the RREF of this augmented matrix. And once we are done with that, you should get something like this. And notice, observing from the solution, we have a vector wherein it makes it linearly dependent. Therefore, we can already say that this set of vectors is not a basis. So to be able to find out whether this vector can be turned into a basis or can make it linearly independent, we can eliminate this vector in particular, or eliminating vector number 4. And in fact, we can actually use these 3 vectors remaining to create not only a linearly independent set of vectors, but also it would be a spanning set. Considering that it would be linearly independent, that means there is only one and one way to be able to represent the zero vector, and that would mean that all the constants or scalars are 0. And therefore, we can apply that principle to other vectors in that vector in the R3 vector space, which would mean that it would also span R3 as well. So next, we have the concept of the dimension. A dimension is the number of vectors in a basis for a vector space V. And for trivial vector spaces, it is 0. So in a dimension, we have, for example, dimension of Rn, then its dimension will be equal to n. Similarly, if you're trying to take for the dimension of the set of m by n matrices, it's equal to m times n. And again, for trivial vector spaces, it is equal to 0. So the dimension containing the 0 vector is just 0. And this property is actually useful once we discover the theorem later on. We also have then the nullity defined as the dimension of the null space of an n by n matrix A. So in a row space, we have, or column space, we have the subspace of Rn spanned by the row or column vectors of the same m by n matrix. And the rank then would be called as the dimension of the row or column space of an m by n matrix. So let's have this theorem, where a linear system, A times X is equal to B, is consistent if and only if B is in the column space of A. So how do we then show that this one is or holds for any vector B? So we know that in this example, this can be shown by the following explanation. So A, we assume it to be an m by n matrix multiplied by a vector x, which is an n by 1 matrix, which should get you to B, an m by 1 vector. And from here, we can multiply A by x and get to a linear system. And in this linear system, we will get actually from the linear system, we will actually get a linear combination. And that would look something like this. X1, and assuming that let's assume that A is basically all vectors or contains vectors as its columns. So V1, V2, all the way until Vn. And from here, we're actually trying to multiply X1, V1, X2, V2, all the way until X sub n, V sub n. And as you can see, it is a linear combination. And based from the theorem a while ago, we know that that there must be one and only one way to show that depending on the scalars that are chosen, you can represent exactly one vector, which is B. And because of this, we can show that it is part of the column space of A, but when there is a solution for the values of the scalars. And from there, we're actually trying to show that these set of vectors are able to, depending on whatever the value of x is, you are able to create this vector B. Meaning, since the column space is defined to be the subspace spanned by the column vectors, and if you are able to find a solution that could get you to this vector B, then therefore B is part of the column space of A. Consequently, the linear system would also then be consistent. So here are some other theorems that need to be taken into consideration. The elementary row operations do not change the null space or the row space of a matrix. And additionally, given a matrix which is in row echelon form, then the row vectors containing the leading ones form the basis for the row space, and the columns with the leading ones form the basis for the column space of that said matrix. So here's an example that makes use of that theorem. So here we are tasked to identify the rank and the nullity of the matrix. So first, to be able to find the rank and the nullity of the matrix, we need to set up the augmented matrix. So what we need to do is, first, which is shown by 1, 3, 2, 2, 2, negative 1, 0, negative 1, 0, and 3, 0, negative 1, 3, 0, 1, and 0, 0, 0. The reason we're looking for 0, 0, 0 at the end at the augmented matrix is because we're trying to find for the nullity, which is the subspace of all the null or the dimension of the null space of a matrix. So we're making use of the null space to be able to find the nullity of the matrix. And from there, we take the RREF form of this matrix. So previously, you saw that the theorem requires the REF form of the matrix. However, we are trying to use the RREF form. And remember, in an RREF matrix, the first property that an RREF matrix should satisfy is that it is in row echelon form or in REF form. Therefore, the RREF form, reduced row echelon form, is also in REF form. So in this case, when we take the RREF form of this matrix, augmented matrix, we get something like this. And based on the theorem a while ago, it says that the columns with the leading ones are said to be the column part of the column space. So these the natural basis vectors over here would be then the part of the column space. And then for the row vectors, since we have these three over here, these would then be part of the row space. Additionally, that would mean that your rank, for the row rank in particular, it's equal to 3. And the column rank is equal to 3 as well. Another thing is to see what the nullity of the matrix is. So notice in this augmented matrix, we have one vector which requires its solution to be part of the other scalars. So when we try to find for the solution of the null space, we can multiply it by A, B, C, D as their constants to this matrix in particular, which would get you A plus D is equal to 0, B plus D is equal to 0, C plus 5D is equal to 0, and D is any real number. With this, we can get the values of A, B, and C, where A is equal to negative D, B is equal to negative D, C is equal to negative 5D. And from there, we can create the null space by taking D as the constant, multiplying it to negative 1, negative 1, negative 5, and 1. Where D is again a real number. Therefore, when we get this vector, this is actually your null space. And because of this, the dimension of the null space would then be equal to 1, or your nullity then would be equal to 1. So that is how you find for the rank and the nullity of a matrix. So here are some other theorems to consider as well or to remember. If two m by n matrices A and B are row or column equivalent, then their row or column spaces are equal. So what do we mean by this? To get to A, from A, for example, we want to get to row matrix B. Then we apply an elementary row operation consecutively. So let's consider this as E sub 1, and another elementary row operation, E sub 2, and so on and so forth, until you get to matrix B. And for every matrix that you encounter after applying an elementary row operation, then we could say that their row or column spaces are equal, which would mean that if we are trying to take the rank of the row and the rank of a column space, and since the row or column spaces are equal, therefore their ranks should also be equal. From here on, the rank would then be just named as the can either pertain on the row or column spaces. It doesn't matter since again their values are equal. And here, if let's for example say that A is a square matrix where M and N are equal in terms of their dimensions, and we want to get to the matrix I sub n. Notice that their row and column spaces are actually equal. As we have shown a while ago, our row and column spaces would then be equal. In specifically the column vectors, since these are all part of the identity matrix, and their column spaces are basically each and every column in that said matrix. So this would then be the column space for both I sub n and the matrix that we have shown a while ago. Let's call this matrix A. So notice that their columns are actually equal. Their column spaces are equal. So with that, it shows the relationship between matrix A and the identity matrix. Here are some more important theorems. The dimension of the row rank and column rank of an n by n matrix A are equal, as shown a while ago. One of the most important theorems in terms of this topic is the rank and nullity theorem. If A is an m by n matrix, then the rank plus nullity is equal to the number of columns in A matrix. Lastly, if A is part of the n by n matrices or square matrices of order n, then rank A is equal to n if and only if A is row equivalent to I sub n, as we have shown a while ago with the example. So here we have again the same previous example, and we have shown that our rank was equal to 3. And our nullity, which is equal to 1, when you add them together, it's actually the number of columns that we have in the matrix 4. So we have 4 columns over here. So that means that the rank nullity theorem should hold all the time. And with these theorems arise some other important properties that we need to remember. A is non-singular if and only if rank A is equivalent to n. Another important corollary or something to remember is that if A is a square matrix, then rank A is equal to n if and only if the determinant is non-zero. The homogeneous system, A times x is equal to 0, has a non-trivial solution if and only if the rank is less than the number of columns. And lastly, given a square matrix, the linear system A times x is equal to B has a unique solution for every n by 1 matrix B if and only if the rank is equal to the number of columns. So let's see some corollaries to be able to answer some of these examples. So here we have the given matrix, and we want to know if it's non-singular. Based from what you've learned from matrices and determinants, you can actually determine whether this matrix is non-singular by simply taking out its determinant. If the determinant is 0, therefore it is not non-singular. Meanwhile, if it is equal or if the determinant in particular is non-zero, then it is non-singular. But we won't use these techniques, and we will make use of the rank to be able to find whether this matrix is non-singular or not. So first, we basically take the inverse of the matrix. And from there, we can try to observe the results. So when we take the inverse of this matrix, we will actually get something like this. So notice that we have gotten the identity matrix. And with this tells us that the rank A is equal to n, based on what we see on the column space or row space. In addition to that, the fact that it is non-singular would mean one thing, and that is that it is that rank A is equal to n, so therefore, it is indeed non-singular. So for the next item, we want to find if this matrix has a non-trivial solution. And based from the corollary a while ago, for it to be non-trivial, we should show that the rank is less than the number of columns that it has. So again, in this example, we want to first make use of this matrix to find out if it's non-trivial or not. And we can do that by showing this, by taking the RREF of this matrix, which should get you to something like this. And from there, once we get the RREF of this matrix, we can show that the rank is actually equal to 2. So, in this example, since the rank is 2 and so is the row, therefore, it has 2. And since the number of columns is equal to 3, which is less than 2 is less than 3, therefore, it has a non-trivial solution. And for it to be non-trivial, again, based from what you've learned from matrices, multiplying this matrix by some value x equal to 0, x over here should be a non-zero vector for it to be non-trivial. So in the next example, we have a theorem that would show the next example. So a linear system has a solution if and only if the rank is equal to the rank of the augmented matrix. So let's show that in this next example. So we want to show if this linear system is said to be consistent or there is a solution to this example. So in this example, we want to find if it's consistent. So first, create the augmented matrix. And this augmented matrix would be the entire matrix on the left-hand side, or your A. And then on the right-hand side would be the matrix which is your B, where B is again -1, -13, and 3. The second is to take the RREF of both A and the RREF as well of the augmented matrix. And then from there, if they are equal, then that means there is a solution, or it is consistent. But if it's not equal, then there is no solution, or it's inconsistent. Or it is again inconsistent. So when we take the REF of both matrices, one augmented, one is the coefficient matrix, we get something like this. So although it looks complicated, what we need to look for, or to look specifically, is on this part and this part alone. So here, the rank of REF is equal to 3. And the rank of this one is also equal to 3. Therefore, since the ranks are equal, that means it is in fact consistent, or the linear system is consistent, or has a solution to this given example. So now let's make use of everything that we have learned from matrices, determinants, and vectors and vector spaces, which all are interconnected with one another. So first, we have the fact that A is non-singular. Before we start actually, please take note that A is an n by n matrix. Okay, so here we have matrix A, which is said to be non-singular, which would mean that there exists a matrix B such that when we multiply it, depending on whichever goes first, gives you the identity matrix. And because of this, we can connect this to the other facts over here. Like, for example, fact number 3, A is row or column equivalent to I sub n, which would mean that when we have the n by 2 by n matrix, n by 2 times n matrix, we should get to the identity matrix. So this one is the identity matrix, and your your original matrix and your I sub n are the identity matrix. When you do enough elementary row operations, you should get the identity matrix and the inverse of that said matrix. And because of this, that would mean that fact number 4 would follow, wherein the linear system has a unique solution for every n by 1 matrix B, meaning x would then be equal to a raised to, or the inverse of a, times b. And this would be holding for every whichever, or the solution would be unique because the inverse of a is always unique. So therefore, the solution would always be unique as well. And because we're able to transform A to an inverse matrix, therefore A is a product of elementary matrices, wherein you multiply different matrices which have elementary row operation or operations applied to each and every matrix, such that when you multiply them all together will give you A, the matrix A. And because based on fact number 4, we know that the linear system has a unique solution, therefore A times x equals 0, the homogeneous system would only have one solution, and that is the trivial solution, wherein x is equal to 0, given A times x is equal to 0. And because it's non-singular in nature, therefore, based on fact number 6, the determinant would also be non-zero as well. So fact number 1 and 6 are actually connected to each other. So these are the facts that you already know from matrices and determinants, which would then all point to other facts that we have just currently discussed. Based from what we've learned from facts number 1, 2, from facts number 1, that it's non-singular, its determinant is non-zero, it has the trivial solution, and additionally, it's a product of elementary matrices, would all point to the fact that the rank is equal to the number of columns. And because of this, we mentioned from fact number 2 that A times x equals 0 has the trivial solution, where x is equal to 0, which would mean that the null space would only consist of 0. And therefore, the nullity, or the dimension of this one in particular, is equal to 0, following fact number 8. And using fact number 7 and 8, combining these would give you the rank and nullity theorem, where n, rank of A, which is n, plus the nullity of A, which is 0, is equal to n. And to be able to get the rank in for this to hold, the row vectors or column vectors of A form a linearly independent set of vectors and also span Rn. And using fact number 9 and 10, these are consequently show that these are bases for Rn. So fact number 9 and 10 are associated with fact number 11 and 12. So that shows the connections between these facts that you have learned before and the facts that we have learned today between matrices, determinants, and vector spaces. Additionally, there's also some sort of connection between the row space, column space, and the null space altogether. So here we have the row space and the null space of A. So based from what we've learned from one theorem, that the row B being part of a column space has a unique solution, which is x sub r. And in addition to that, we also have the null space of A, wherein when you multiply to A, it is equal to the 0 vector. One thing that you should also take note is that A is an n by n matrix, which is why you can see from on the right hand side we have Rm and Rn on opposite sides of the image. So what is the connection of all of these columns, rows, and null spaces all together? So based from this one is what we've shown a while ago in the theorem, wherein it's consistent if B is part of the column space. And in addition to that, when we have the null space over here, x of n when multiplied by a should give you the zero vector, which is basically only the zero vectors. Okay, so here we also have x equals to x sub r plus x sub n. So what does this have to do with anything? It looks like it is out of place. And a sub x is equal to b. So how do we show that it actually holds with this property? A, we can expand x to be x sub r plus x sub n and distribute it based from the properties of matrices, giving you this equation. And we know that a times x sub r is equal to b, and a times x of n gives you the zero vector. Therefore, it does indeed equal to b. And because you can see that there is a right angle here, that means they are orthogonal with one another, or they're perpendicular with one another, such that when you multiply the row space and the null space, it should get you to the zero vector right at this point. And you can also see that their dimensions are equal for the row and column space, known as dimension R. In addition to that, we also have the dimensions m minus r and n minus r. But these seem look like they're out of place, right? So remember the rank nullity theorem, wherein rank plus nullity is equal to n. Therefore, in an Rn space, rank is r plus n minus r as your nullity, which equals to n. Similarly, rank r plus the nullity dimension m minus r is equal to m. Thus, it's the number of columns in this space. So additionally, what you want to consider is that the null space of A transpose is basically part, or it helps in finding out the row or column space. So if we have for example, a matrix 1, 2, 3, and 4, 5, 6, the row space would basically consider all the rows here, and the column space would consist of all the columns over here. And taking the transpose of this matrix would give you the null space of either the row vectors or the column vectors. So overall, that is the interconnection or relationships between the concept of basis, rank, dimension, and in addition to that, determinants, inverse matrices, and even spanning sets, linear independence, and the concept of subspaces as well.